Now let's compare the designs head-to-head in their outputs and the inputs that they required. So their responses are a little bit different, a bigger overshoot in design 1 than design 2, and a higher rise time in design 2 than design 1, but they're fairly close to each other. If we look at the input voltages, at least visually, they both have that initial kick that go up to that 20 volts because that was the saturation point that I put into the Simulink model. But after that initial kick, we see that their peaks are fairly similar, probably going up to around 14 volts and then leveling off after that. So they both get to the 5 volts in the output, given it enough time. They're both underdamped systems. So let's see, how does it compare back to originally how we wanted the system to behave? Right, so remembering all the way back to the point of this is we wanted a steady state voltage of 5 volts, and we wanted our max overshoot to be exactly 18% and the rise time to be 0.75 seconds. So if we look at the two designs, on max overshoot, design number 1 came pretty close, 18.4. It's a little more than what we wanted. Design 2 is 1% point less than what we wanted. And both of our rise times are smaller than the 0.75. Design 2, its rise time's a little bit closer, whereas with design 1, its overshoot was a little bit closer. So for the two designs that were kind of chosen arbitrarily, at least what the zeros of the controller were, neither design matched our desired response. Now, these were only two of an infinite number of designs we could have had for our controller. I could have chosen an infinite number of zeros for my controller, and each one would have at least slightly had different max overshoots after simulation and rise times after simulation. So if I really was concerned about not matching my design parameters, the 18% and the 0.75 seconds of rise time, well, I would need to design 3, 4, I would need to iterate this, and really effectively what I need to do is change what the 3 gains are in the controller. Again, the step of going through and picking zeros for the controller and then using the root locus, ultimately all that is doing is changing the 3 gains in my PID controller. So very likely there is a better combination of the 3 gains out there, at least in terms of getting me closer to those desired response parameters for this problem. I just need to find what they are. And starting with the root locus method got us fairly close for our initial design, but not exactly there. So from here, I would probably want to use a different method in order to get closer to my desired response parameters. So maybe I want to start with the 3 gains I found with the root locus method and then try adding or subtracting a little bit of gain from each of them and seeing if I can get a little bit closer to what I want. But on the next slide, I'll talk about more refined methods to do that. All right, so again, going back to the closed loop transfer function, we were able to find it for both of the designs, but we had those 2 left half plane zeros. And they were complex conjugates of each other. They were both complex numbers. So in theory, we can't really get a good sense of how close is our 2-0 2-pole system going to behave in relation to how the just 2-pole system would behave, that baseline. But the root locus method is designing it based on how does the baseline second order system behave. So we're not that close to it. We can't use what we know from Unit 2 because of those 2 complex zeros that we're adding. We also saw in these, I put in that saturation, that limiter of what the max voltage could be. So our system isn't even going to behave like the closed loop transfer function because that did not take into account the limitation on the maximum voltage for the input, but the Simulink model did. So there's a second difference in there of how we got these max overshoots and rise time because these were found with the saturation. If we just looked at the closed loop transfer functions, those would not have the saturation. So what we're seeing here is really a limitation on the root locus method. For the PD controller, it works pretty well. For a lag compensator or a lead compensator, it can work pretty well because we're adding just 1 real 0 into our system, and it's going to behave fairly similarly to the baseline system. For the PID, it starts to break down when we add these multiple zeros into our closed loop transfer function, especially when those zeros are complex conjugates of each other. But it does show it's a starting point, but what we need to always do is we need to validate our design in simulation, because it's different than the baseline. It's different even than the closed loop transfer function that we developed if we're including that saturation point. So the simulation is going to really tell us how is this going to work in a real system, and is it close enough to what we desire. So these two designs, we didn't really get the response that we wanted. So what else can we do? Well, we can do what's called PID tuning. Again, we have a continuum of choices we could have made for those zeros, which results in a continuum of choices we can make for the three gains in our PID system. And we saw that depending on what those gains were, the responses were a little bit different in terms of here, max overshoot and rise time, but also peak time, settling time, other things we might be interested in. And ultimately, there's different control efforts required depending on what the gains are that we chose. So I won't go into great detail here, but one method for choosing what those three gains are, rather than using a root locus method, is we can use the Ziegler-Nichols method, which is kind of a more experimental way of finding what the three gains should be. So in short, what it's doing is finding one gain at a time and setting it, and now introducing a second gain, setting it, and then finding what the third gain is, and then setting it. So it's a little bit more systematic a way of doing it. So when we know the plant, like we did in this example, Ziegler-Nichols method can get us a good combination of gains to use. It's also good when the plant is unknown and we have a PID controller on it. So if we have a very complex system that we want to try to control with a PID in real time, a Ziegler-Nichols method can get us gains that can control the system and get us the type of performance that we're looking for. And there's other methods as well, other than Ziegler-Nichols, that we can use for testing these gains and finding which combination is optimal. And there's all sorts of literature you can look at that might give you different methodologies to use. Another thing we didn't observe here, but in real systems is going to be a concern, is that derivative term that we're using is highly susceptible to any noise we have in the measurement. All of the simulations we've done, all of the systems we looked at in this unit, we've had perfect sensing, perfect actuation. There was no noise in any of the measurements that we had. Once we introduce a little bit of noise, this derivative term can get very, very large because we're going to have sudden jumps in the values that we're measuring. So it's something to be aware of when we're using a derivative control as part of our controller scheme, is how can we smooth it out, or how can we reduce the noise, or how can we limit extreme changes in the derivative control that's being exerted.